Welcome back to Crystallography for everyone. In the last video, we saw the basic construction of a 2D lattice. We defined a lattice vector A and a lattice vector B, and we defined the angle between them. In this video, we are going to look at the different types of 2D lattices. We saw how alpha can take on any angle, and there are specific values of alpha, of A, and of B that have names. So in this video, we're going to go over them. They happen to be called Bravais lattices. Bravais lattices. They were first shown by Auguste Bravais. He's a French physicist in the 1800s, and so they're named after him. We already saw one type of Bravais lattice, known as the parallelogram. In this case, I will draw the translation vectors, A and B. In this case, A and B are not equal. I should say that the magnitude of A is not equal to the magnitude of B. And alpha is not equal to 90 degrees. When alpha is equal to 90 degrees and A and B are equal, that is reserved for another type of Bravais lattice. This Bravais lattice is the parallelogram. And just in case you forgot, this vector is A and this vector is B. I can also define a rectangular Bravais lattice. Rectangular. In this case, A is not equal to B, and alpha is equal to 90 degrees. So I'll draw B, and I'll draw A, and this defines a rectangular lattice. Where this angle here, alpha, is 90 degrees. Remember, this lattice extends off onto a 2D plane. It is infinite and periodic. I can get between any point with a vector consisting of linear combinations of A and B. Just to reinforce that. This is a rectangular lattice. This is a parallelogram lattice. I can also define what is known as a centered rectangular lattice. This this first one we showed is actually known as a primitive rectangular lattice. We will look more on that later when we talk about unit cells. But a centered rectangular lattice has the same restrictions as the parallelogram. A is not equal to B, alpha is not equal to 90 degrees. But when I arrange all of my points, what we see is a structure like this. So I think you can kind of compare these two. You can see this rectangle here. You can also see a similar rectangle in this lattice. But there's a point at the center, and that is where our lattice vector B is pointing to. Here's A. So this is known as a centered rectangular lattice. So I'm running out of space here, so I will erase some of what we've shown to show you the last two Bravais lattices in 2 dimensions. We also have a square lattice. In this case, alpha is equal to 90 degrees, and I think you can guess that the magnitude of A is equal to the magnitude of B. In this case, so I will draw out B and A, trying to make them roughly the same, trying to make them exactly the same. I'll draw out the lattice points once again. Going off to infinity. So here is our 2-dimensional square lattice. Alpha is 90 degrees, and A and B are equal in magnitude. Square lattice. Our final Bravais lattice in 2 dimensions is known as the Rhombus Lattice. In this case, A, the magnitude of A is equal to the magnitude of B, and alpha is equal to 60. So we can draw that like so. And we can distribute our lattice points. Keep showing the same number for consistency. Extends off to infinity. And our angle is equal to 60. This forms a rhombus. And I would like to point out, we also see this centered hexagon here. So sometimes this is also known as a centered hexagonal lattice. Centered. But most of the time, we'll call it a rhombus. So in the next video, we are going to leave flatland, we're going to leave the 2D lattices behind and start talking about 3D lattices. I hope to see you there.